Affective computing is the study and development of systems and devices that can recognize, interpret, process, and simulate human affects. It is an interdisciplinary field spanning computer science, psychology, and cognitive science. While the origins of the field may be traced as far back as to early philosophical inquiries into emotion, the more modern branch of computer science originated with Rosalind Picard's 1995 paper on affective computing. A motivation for the research is the ability to simulate empathy. The machine should interpret the emotional state of humans and adapt its behavior to them, giving an appropriate response for those emotions. Areas: detecting and recognizing emotional information. Detecting emotional information begins with passive senses which capture data about the user's physical state or behavior without interpreting the input. The data gathered is analogous to the cues humans use to perceive emotions in others. For example, a video camera might capture facial expressions, body posture, and gestures, while a microphone might capture speech. Other sensors detect emotional cues by directly measuring physiological data, such as skin temperature and galvanic resistance. Recognizing emotional information requires the extraction of meaningful patterns from the gathered data. This is done using machine learning techniques that process different modalities, such as speech recognition, natural language processing, or facial expression detection, and produce either labels or coordinates in a valence arousal space. Emotion in machines. Another area within affective computing is the design of computational devices proposed to exhibit either innate emotional capabilities of that are capable of convincingly simulating emotions. A more practical approach, based on current technological capabilities, is the simulation of emotions in conversational agents in order to enrich and facilitate interactivity between human and machine. While human emotions are often associated with surges in hormones and other neuropeptides, emotions in machines might be associated with abstract states associated with progress in autonomous learning systems. In this view, affective emotional states correspond to time derivatives in the learning curve of an arbitrary learning system. Marvin Minsky, one of the pioneering computer scientists in artificial intelligence, relates emotions to the broader issues of machine intelligence, stating in The Emotion Machine that emotion is not especially different from the processes that we call thinking. Technologies. In cognitive science and neuroscience, there have been two leading models describing how humans perceive and classify emotion: the continuous and the categorical model. The continuous model defines each facial expression of emotion as a feature vector in a face space. This model explains, for example, how expressions of emotion can be seen at different intensities. In contrast, the categorical model consists of classifiers, each tuned to a specific emotion category. This model explains, among other findings, why the images in a morphing sequence between a happy and a surprise face are perceived as either happy or surprise but not something in between. These approaches have one major flaw in common: they can only detect one emotion from an image. This is generally done by a winner-takes-it-all method. Yet, every day we can perceive more than one emotional category from a single image. Both the categorical and continuous model are unable to identify multiple emotions. So a new way to model it is to consider new categories as overlap of a small set of categories. A detailed study related to this topic is given in A Model of the Perception of Facial Expressions of Emotion by Humans. Research Overview and Perspectives. The following sections consider the possible features which can be used for the task of emotion recognition. Emotional speech. One can take advantage of the fact that changes in the autonomic nervous system indirectly alter speech, and use this information to produce systems capable of recognizing affect based on extracted features of speech. For example, speech produced in a state of fear, anger, or joy becomes faster, louder, precisely enunciated with a higher and wider pitch range. Other emotions such as tiredness, boredom, or sadness lead to slower, lower pitched and slurred speech. Emotional speech processing recognizes the user's emotional state by analyzing speech patterns, vocal parameters, and prosody features such as pitch variables and speech rate are analyzed through pattern recognition. Speech recognition is a great method of identifying affective state, having an average success rate reported in research of 63%. This result appears fairly satisfying when compared with humans' success rate at identifying emotions, but a little insufficient compared to other forms of emotion recognition. Furthermore, many speech characteristics are independent of semantics or culture, which makes this technique a very promising one to use. Algorithms. The process of speech-text affect detection requires the creation of a reliable database, knowledge base, or vector space model, broad enough to fit every need for its application, as well as the selection of a successful classifier which will allow for quick and accurate emotion identification. Currently, the most frequently used classifiers are linear discriminant classifiers, k-nearest neighbor, Gaussian mixture model, support vector machines, artificial neural networks, decision tree algorithms, and hidden Markov models. Various studies showed that choosing the appropriate classifier can significantly enhance the overall performance of the system. The list below gives a brief description of each algorithm. LDC classification happens based on the value obtained from the linear combination of the feature values, which are usually provided in the form of vector features. KNN classification happens by locating the object in the feature space and comparing it with the k-nearest neighbors. The majority vote decides on the classification. GMM is a probabilistic model used for representing the existence of subpopulations within the overall population. Each subpopulation is described using the mixture distribution, which allows for classification of observations into the subpopulations. SVM is a type of linear classifier which decides in which of the two possible classes each input may fall into, and is a mathematical model inspired by biological neural networks that can better grasp possible non-linearities of the feature space. Decision tree algorithms work based on following a decision tree in which leaves represent the classification outcome, and branches represent the conjunction of subsequent features that lead to the classification. HMMs are a statistical Markov model in which the states and state transitions are not directly available to observation. Instead, the series of outputs dependent on the states are visible. In the case of affect recognition, the outputs represent the sequence of speech feature vectors, which allow the deduction of states as sequences through which the model progressed. The states can consist of various intermediate steps in the expression of an emotion, and each of them has a probability distribution over the possible output vectors. The states as sequences allow us to predict the affective state which we are trying to classify, and this is one of the most commonly used techniques within the area of speech affect detection. It is proved that having enough acoustic evidence available, the emotional state of a person can be classified by a set of majority voting classifiers. The proposed set of classifiers is based on three main classifiers: KNN, C4.5 and SVM-RBF kernel. This set achieves better performance than each basic classifier taken separately. It is compared with two other sets of classifiers, one against all multi-class SVM with hybrid kernels and the set of classifiers which consists of the following two basic classifiers, C5.0 neural network. The proposed variant achieves better performance than the other two sets of classifiers. Databases. The vast majority of present systems are data-dependent. This creates one of the biggest challenges in detecting emotions based on speech, as it implicates choosing an appropriate database used to train the classifier. Most of the currently possessed data was obtained from actors and is thus a representation of archetypal emotions. Those so-called acted databases are usually based on the basic emotions theory, which assumes the existence of 6 basic emotions, the others simply being a mix of the former ones. Nevertheless, these still offer high audio quality and balanced classes, which contribute to high success rates in recognizing emotions. However, for real-life application, naturalistic data is preferred. A naturalistic database can be produced by observation and analysis of subjects in the natural context. Ultimately, such database should allow the system to recognize emotions based on the context as well as work out the goals and outcomes of the interaction. The nature of this type of data allows for authentic real-life implementation, due to the fact it describes states naturally occurring during the human-computer interaction. Despite the numerous advantages which naturalistic data has over acted data, it is difficult to obtain and usually has low emotional intensity. Moreover, data obtained in a natural context has lower signal quality, due to surroundings noise and distance of the subjects from the microphone. The first attempt to produce such database was the FAU-IBO Emotion Corpus for CEICES, which was developed based on a realistic context of children playing with Sony's IBO robot pet. Likewise, producing one standard database for all emotional research would provide a method of evaluating and comparing different effect recognition systems. Speech descriptors. The complexity of the effect recognition process increases with the amount of classes and speech descriptors used within the classifier. It is therefore crucial to select only the most relevant features in order to assure the ability of the model to successfully identify emotions, as well as increasing the performance, which is particularly significant to real-time detection. The range of possible choices is vast, with some studies mentioning the use of over 200 distinct features. It is crucial to identify those that are redundant and undesirable in order to optimize the system, and increase the success rate of correct emotion detection. The most common speech characteristics are categorized in the following groups: frequency characteristics, accent, shape, affected by the rate of change of the fundamental frequency. Average pitch, description of how high, low the speaker speaks relative to the normal speech. Contour slope, describes the tendency of the frequency change over time. It can be rising, falling a level. Final lowering, the amount by which the frequency falls at the end of an utterance. Pitch range, measures the spread between maximum and minimum frequency of an utterance. Time-related features. Speech rate, describes the rate of words or syllables uttered over a unit of time. Stress frequency, measures the rate of occurrences of pitch-accented utterances. Voice quality parameters and energy descriptors. Breathiness, measures the aspiration noise in speech. Brilliance, describes the dominance of higher-low frequencies in the speech. Loudness, measures the amplitude of the speech waveform, translates to the energy of an utterance. Pause discontinuity, describes the transitions between sound and silence. Pitch discontinuity, describes the transitions of the fundamental frequency. Dot. Facial effect detection. The detection and processing of facial expression is achieved through various methods such as optical flow, hidden Markov model, neural network processing, or active appearance model. More than one modalities can be combined or fused to provide a more robust estimation of the subject's emotional state. Facial expression databases. Creation of an emotion database is a difficult and time-consuming task. However, database creation is an essential step in the creation of a system that will recognize human emotions. Most of the publicly available emotion databases include posed facial expressions only. In posed expression databases, the participants are asked to display different basic emotional expressions, while in spontaneous expression database, the expressions are natural. Spontaneous emotion elicitation requires significant effort in the selection of proper stimuli, which can lead to a rich display of intended emotions. Secondly, the process involves tagging of emotions by trained individuals manually, which makes the databases highly reliable. Since perception of expressions and their intensity is subjective in nature, the annotation by experts is essential for the purpose of validation. Researchers work with three types of databases, such as database of peak expression images only, database of image sequences portraying an emotion from neutral to its peak, and video clips with emotional annotations. Many facial expression databases has been created and made public for expression recognition purpose. Two of the widely used databases are CK+ and Jaffe. Emotion classification by doing cross-cultural research in Papua New Guinea on the four tribesmen. At the end of the 1960s, Paul Ekman proposed the idea that facial expressions of emotion are not culturally determined, but universal. Thus, he suggested that they are biological in origin and can therefore be safely and correctly categorized. He therefore officially put forth 6 basic emotions in 1972: anger, disgust, fear, happiness, sadness, surprise. However, in the 1990s, Ekman expanded his list of basic emotions, including a range of positive and negative emotions, not all of which are encoded in facial muscles. The newly included emotions are amusement, contempt, contentment, embarrassment, excitement, guilt, pride in achievement, relief, satisfaction, sensory pleasure, shame. Facial action coding system defining expressions in terms of muscle actions. A system has been conceived in order to formally categorize the physical expression of emotions. The central concept of the facial action coding system, or FACS, as created by Paul Ekman and Wallace V. Friesen in 1978, are action units. They are basically a contraction or a relaxation of one or more muscles. However, as simple as this concept may seem, it is enough to form the base of a complex and devoid of interpretation emotional identification system. By identifying different facial cues, scientists are able to map them to the corresponding action unit code. Consequently, they have proposed the following classification of the 6 basic emotions according to their action units. Challenges in facial detection. As with every computational practice, in effect detection by facial processing, some obstacles need to be surpassed. In order to fully unlock the hidden potential of the overall algorithm or method employed, the accuracy of modeling and tracking has been an issue, especially in the incipient stages of affective computing. As hardware evolves, as new discoveries are made and new practices introduced, this lack of accuracy fades, leaving behind noise issues. However, methods for noise removal exist, including neighborhood averaging, linear Gaussian smoothing, median filtering, or newer methods such as the bacterial foraging optimization algorithm. It is generally known that the degree of accuracy in facial recognition has not been brought to a level high enough to permit its widespread, efficient use across the world. Without improving the accuracy of hardware and software used to scan faces, progress is very much slowed down. Other challenges include the fact that posed expressions, as used by most subjects of the various studies, are not natural, and therefore not 100% accurate. The lack of rotational movement freedom. Affect detection works very well with frontal use, but upon rotating the head more than 20 degrees there have been problems. Body gestures can be efficiently used as a means of detecting a particular emotional state of the user, especially when used in conjunction with speech and face recognition. Depending on the specific action, gestures could be simple reflexive responses, like lifting your shoulders when you don't know the answer to a question, or they could be complex and meaningful, as when communicating with sign language. Without making use of any object or surrounding environment, we can wave our hands, clap or beckon. On the other hand, when using objects, we can point at them, move, touch or handle these. A computer should be able to recognize these, analyze the context and respond in a meaningful way, in order to be efficiently used for human-computer interaction. There are many proposed methods to detect the body gesture. Some literature differentiates two different approaches in gesture recognition: a 3D model-based and an appearance-based. The foremost method makes use of 3D information of key elements of the body parts in order to obtain several important parameters, like palm position or joint angles. On the other hand, appearance-based systems use images or videos for direct interpretation. Hand gestures have been a common focus of body gesture detection. Apparentness methods and 3D modeling methods are traditionally used. Physiological monitoring. This could be used to detect a user's emotional state by monitoring and analyzing the physiological signs. These signs range from the pulse and heart rate to the minute contractions of the facial muscles. This area of research is still in relative infancy, as there seems to be more of a drive towards affect recognition through facial inputs. Nevertheless, this area is gaining momentum and we are now seeing real products which implement the techniques. The three main physiological signs that can be analyzed are blood volume, pulse, galvanic skin response, facial electromyography. Blood volume pulse. Overview. A subject's blood volume pulse can be measured by a process called photoplethysmography, which produces a graph indicating blood flow through the extremities. The peaks of the waves indicate a cardiac cycle where the heart has pumped blood to the extremities. If the subject experiences fear or is startled, the heart usually jumps and beats quickly for some time, causing the amplitude of the cardiac cycle to increase. This can clearly be seen on a photoplethysmograph when the distance between the trough and the peak of the wave has decreased. As the subject calms down, and as the body's inner core expands, allowing more blood to flow back to the extremities, the cycle will return to normal. Methodology. Infrared light is shone on the skin by special sensor hardware, and the amount of light reflected is measured. The amount of reflected and transmitted light correlates to the BVP as light is absorbed by hemoglobin, which is found richly in the blood stain. Disadvantages. It can be cumbersome to ensure that the sensor shining infrared light and monitoring the reflected light is always pointing at the same extremity, especially seeing as subjects often stretch and readjust the position whilst using a computer. There are other factors which can affect one's blood volume pulse, as it is a measure of blood flow through the extremities. If the subject feels hot or particularly cold, then the body may allow more or less blood to flow to the extremities, all of this regardless of the subject's emotional state. Facial electromyography. Facial electromyography is a technique used to measure the electrical activity of the facial muscles by amplifying the tiny electrical impulses that are generated by muscle fibers when they contract. The face expresses a great deal of emotion. However, there are two main facial muscle groups that are usually studied to detect emotion. The corrugator supercilii muscle, also known as the frowning muscle, draws the brow down into a frown, and therefore is the best test for negative, unpleasant emotional response. The zygomaticus major muscle is responsible for pulling the corners of the mouth back when you smile, and therefore is the muscle used to test for positive emotional response. Galvanic skin response. Galvanic skin response is a measure of skin conductivity, which is dependent on how moist the skin is, as the sweat glands produce this moisture and the glands are controlled by the body's nervous system. There is a correlation between GSR and the arousal state of the body. The more aroused a subject is, the greater the skin conductivity and GSR reading. It can be measured using two small silver chloride electrodes placed somewhere on the skin, and applying small voltage between them. The conductance is measured by a sensor. To maximize comfort and reduce irritation, the electrodes can be placed on the feet, which leaves the hands fully free to interface with the keyboard and mouse. Visual aesthetics. Aesthetics, in the world of art and photography, refers to the principles of the nature and appreciation of beauty. Judging beauty and other aesthetic qualities is a highly subjective task. Computer scientists at Penn State treat the challenge of automatically inferring aesthetic quality of pictures using the visual content as a machine learning problem, with a peer-rated online photo-sharing website as data source. They extract certain visual features based on the intuition that they can discriminate between aesthetically pleasing and displeasing images. Potential applications. In e-learning applications, affective computing can be used to adjust the presentation style of a computerized tutor when a learner is bored, interested, frustrated, or pleased. Psychological health services, i.e. counseling, benefit from affective computing applications when determining a client's emotional state. Robotic systems capable of processing affective information exhibit higher flexibility while one works in uncertain or complex environments. Companion devices, such as digital pets, use affective computing abilities to enhance realism and provide a higher degree of autonomy. Other potential applications are centered around social monitoring. For example, a car can monitor the emotion of all occupants and engage in additional safety measures, such as alerting other vehicles if it detects the driver to be angry. Affective computing has potential applications in human-computer interaction, such as affective mirrors allowing the user to see how he or she performs, emotion monitoring agents sending a warning before one sends an angry email, or even music players selecting tracks based on mood. One idea, put forth by the Romanian researcher Drive Nicu in an interview, is the analysis of a person's face while they are using a certain product. Companies would then be able to use such analysis to infer whether the product will or will not be well received by the respective market. One could also use affective state recognition in order to judge the impact of a TV advertisement through a real-time video recording of that person, and through the subsequent study of his or her facial expression. Averaging the results obtained on a large group of subjects, one can tell whether that commercial has the desired effect and what the elements which interest the watcher most are. Affective computing is also being applied to the development of communicative technologies for use by people with autism.